Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 8cc, Lesson 7 on sums of dice. Now this is really kind of a lesson where you're going to want to have a couple die if you have them. All right, if you don't have them, we do have a random number table that will allow you to kind of simulate this without die, but it's really kind of nice to have a couple of them to roll and see what happens. And the whole point is we're going to be rolling two die, we're going to be looking at the numbers that show up on them, and then we're going to be adding them together and thinking about the probability that we get a particular sum. That's it. And it's a great example of a compound event, right? Because we've got two of these dice, right? And each one of them, it's simple enough to think about in isolation. You know, there's 6 ways this one can come up. There's 6 ways that this one can come up. But thinking about them when we put them together into a compound event becomes a lot trickier. So let's jump right into it. If you do have a pair of dice, that would be awesome. You'll have a lot more fun with this lesson if you do. Rolling 2 dice and finding their sum is a good example of a compound event. It can be done with 2 real dice, or using a random number table, which is attached to this and apparently is missing from my text. I think this is sitting on top of it. The random number table is actually, later on in the lesson. And if you decide to use this instead of actually rolling the die, that's fine. These things are sort of like simulated rolls on the die, all right? And you can kind of use this table by coming up with your birthday. So like my birthday is the 28th. All right, so for me, I might start on the 28th and say, okay, I rolled a 5 and a 4, a 5 and a 2, a 2 and a 3, a 4 and a 4, then I'd go up to the next column, however many rolls I needed. This was a randomly generated table. Let me go back into my full screen and go back. So anyway, you can definitely use those if you need to. Let's take a look at exercise 1. Consider rolling 2 dice and finding the sum of the 2 numbers rolled. Letter A, what are all the possible sums? Right? What are all the possible sums that could come up if I rolled 2 standard dice, each one of them numbered 1 through 6? Pause the video now and write down all the possible sums that could come up. Well, the smallest number that I can get on a given die when I roll it is the number 1. So the smallest sum I could get is if I rolled a 1 on the first die, a 1 on the second die, and when I added them together, I'd get a sum of 2. Now obviously I can get a sum of 3 by rolling a 2 on one and a 1 on the other, right? So I can get a sum of 3, I can get a sum of 4, etc. In fact, I can get all these sums up to the maximum sum. And what would that be? Well, of course, if I rolled a 6 on one of the die and rolled a 6 on the other die, then when I added them together, I'd get a sum of 12. So all possible sums I could get, right, are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, I want to be very clear about this. These are all the possible events I could have. They are not necessarily equally likely outcomes, okay? They are simply the event of rolling 2 die and getting a sum of an 8, or the event of rolling 2 die and getting a sum of 11, or a sum of 3, or whatever. Now comes you playing around with this, all right? And again, there's no substitute for actually rolling a couple die, adding up, and plotting on a dot plot. So let's take a look at letter B. Either roll 2 dice 30 times or use the random number table to sample 30 dice rolls and find the sums. Create a line plot, a dot plot, of the sums below. If you use the table, simply pick the day of your birth date and move down the table, picking off 30 rolls. So again, just to make sure everybody understands how to use that table, right? If, let's say, you were born on March 8th, let's say you were born on March 8th. Then you'd just go to the 8 and you'd start with 4, 4, right? So that would be a sum of 8. That would be your first roll. Then you'd have a 2 and a 3. That would be a sum of a 5. A 3 and a 2, also a sum of a 5. A 1 and a 6, a sum of a 6, etc. Right? And you'd just kind of go down. If you hit the bottom of the first column, you'd go up to the second column to get your next set of rolls. If for some reason you went through all of those, you'd kind of go here as well. All right. Again, I would highly, highly advise to just roll 2 dice and add them up. All right. Now that's going to take a while because you're going to do it 30 times, and every time you roll, you're not only going to look at the two numbers, but you're going to add them up, and then you're going to put a dot above whatever sum you got. And remember, all of our sums actually go from 2 to 12, so you won't likely have anything for 13, 14, 15, or 1 or 0, but I wanted to have kind of a larger number line. So pause the video now. It might take you up to 10 minutes to do this kind of simulation. Go ahead and do it. Draw your dot plot, and let's see what you have. Now again, absolutely impossible for me to know what results you got. But I actually did this experiment. I took 2 dice out, rolled them, kept adding them up. I did it 30 times, and I got the following dot plot. It's like magic, right? So, I got 1, 3. I didn't get any 2s. Oh, well, what are you going to do? I got 3 sums of 4, 4 sums of 5, 1, 2, 3, 4, 5, 6 sums of 6, etc. I think I got 8 sums of 7 and whatnot. So, based on my results, I'm going to answer these questions. You should answer these questions based on your results, which I'm hopeful are similar to mine. Okay? Similar. But who knows? Take a look at letter C. Sorry, it's like I thought that should be letter B. All right, let's take a look at letter C. What sums are least likely based on your random sample? All right, so I did this random sample, and it's random because I threw dice 30 times, right? So it looks like the sums that were least likely were sums of like 2 and 3, and sums like 10, 11, 12. So maybe I'd say 2, 3, 10, 11, and 12. Those were very unlikely, right? They barely ever happened. I got way more of them in here, and that's, of course, letter D. What sums are the most likely based on your random sample? Well, those are kind of, the sums from 6 to 8, I'm going to say 6 to 8 with 7 being most common. Now, you may not have found that 7 was the most common. Maybe you had more sums of 6 or more sums of 8. For me, my most likely one was a 7. Now, let's talk about a really important piece, letter E. Can you explain why C and D are true? All right, so let's come back and talk about this. In other words, why is it that sums of like 2, 3, 10, 11, 12 were fairly uncommon? Not impossible, right? But uncommon. Whereas sums of 6 to 8 were fairly common, right? There were lots of those, and there were a ton of 7s, right? We hit the 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, is that right? 1, 2, 3, 4, 5, 6, 7, 8. 8 7s. We hit a sum of 7 8 times. So pause the video now and think about why that is. Well, let's just illustrate it with the most common sum that we got, which was 7, and maybe kind of the least common ones, maybe 2 and 12. And I know I didn't hit any 11s, but I could have, right? I could have thrown a 5 and a 6 or a 6 and a 5. And that kind of gets at it, right? Doesn't it? So, for 2 and 12, right, what could we have? Well, for 2, we could just have a 1 and a 1 that we roll. And for 12, the best we could do is a 6 and a 6. There's literally only 2 ways. There's only one way to get a 2. And that's I roll a 1 and then I roll another 1. And there's only one way to get a 12. I roll a 6 and I roll another 6. On the other hand, let's talk about the 7, right? The 7, there's a lot of ways. For a 7, right, I could have gotten what? I could have rolled a 1 and then a 6. I could have rolled a 2 and a 5, a 3 and a 4, etc. Many ways. There's many ways to get a sum of 7, but there's only one way to get a sum of 2. I rolled a 1 and another 1. A 12. I rolled a 6 and another 6. But how can I take this compound event and really find these probabilities? Because this is much more complicated. So let's take a look at it. Here's our random number table. Let's really analyze this thing. Exercise number 2. Finish filling in the following table with ordered pairs where the x-coordinate is the first roll and the y-coordinate is the second roll. Now this is very important, right? So we talked about doing organized lists, tree diagrams, and outcome tables. And that's what we have here. And outcome tables are really, really nice when there's a two-stage event. Roll one die, roll the second die, right? Because then we can represent equally likely outcomes with ordered pairs. Ordered pairs meaning that the first number represents something. It represents what I rolled on die number 1. And the second number in the pair, right, the y-coordinate if you will, represents what I rolled on the second die. So it's really easy to fill in a table like this, right? So 1, 1 means I got a 1 on the first, a 1 on the second. 1, 2 means I got a 1 on the first and a 2 on the second. 1, 3 means I got a 1 on the first, a 3 on the second, and then I could keep going, right? Right, the next one would be getting a 1 on the first and a 4 on the second, a 1 on the first and a 5 on the second, a 1 on the first and a 6 on the second. There's 6 different ways I can get a 1 on the first roll. Right, but I could also get a 2 on the first roll. Now if I got a 2 on the first roll and a 1 on the second roll, that looks a lot like this one, but they're actually distinctly different things, right? Right, this is getting a 2 on the first roll and a 1 on the second. This is getting a 1 on the first and a 2 on the second. Think of it as like having, if I had a green die and a blue die, right? It's different. You know, I might get the same sum, but it's actually a different scenario, 2, 1 than 1, 2. But I could keep filling this in as well, right? So I could have gotten a 2 on the first roll and a 3 on the second, a 2 on the first and a 4 on the second, a 2 and a 5, and a 2 and a 6. All right. By the way, none of these am I doing the sums of yet, but you can think about the sums. Like if you took the 2, 3, that would be a sum of 5, this would be a sum of 6, this would be a sum of 7, this would be a sum of 8, etc. Why don't you pause the video now and fill out the rest of this outcome table to show all the equally likely outcomes. All right, well, I didn't want you to have to listen to me just talk about it as I filled in the rest of these things. So here the rest of them are, right? Again, a 3 and a 2, a 3 and a 3, a 3 and a 4, etc., right? Simple enough. But look at all of these equally likely outcomes. There are a lot of them. But how many are there exactly? Well, I hope you're not going to end up counting every single one of these, but pause the video now and tell me how many outcomes there are in this sample space. All right, so it's simple enough. There's 36 of them. Now, you could literally count them. You could be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. You could do that. But again, the easy way of knowing how many total equally likely outcomes there are in a sample space is say, well, for this simple event, there are 6. For this simple event, there are 6. And so, the total number of outcomes will be 6 times 6, or 36. There are 36 outcomes in this sample space. And each one of those 36 has a sum that goes with it, right? Here's that sum of 2, 1 plus 1. Here's that sum of 12, 6 plus 6, right? If I point at any one of these cells, like if I randomly pointed at that one, 4, 2, that would be a sum of 6. If I went over here and looked at this, 4, 6, that would be a sum of 10. So each one of these 36 has a sum, with many of the sums, obviously, being repeated. So now, let's go to exercise number 3. Now I'm going to have to probably move up and down to take a look at this table, but that's okay. We'll deal with it. We won't get too seasick. Exercise number 3. The table above gives the sample space of equally likely outcomes. Based on the table, answer the following question. Letter A. List all the outcomes that result in a sum of 7. All right, well, let's go up to this table and look for those 7s, right? 7 was the one, at least when I rolled the die, I got more often than any other ones. Well, here's a 7, right? 6, 1. Here's a 7, 5, 2. Here's a 7, 4, 3. Isn't that kind of nice, right? All of these have the same sum. By the way, you would notice that anywhere. Like if I went here, 6, 4, 5, 5, 4, 6, all of them along this diagonal have a sum of 10, right? I could come here and I could say, all of them along this diagonal right? Have a sum of 6, all of them along this diagonal. Have a sum of 8, right? So the diagonals actually kind of contain, the diagonals going this way, not going this way. The diagonals going this way contain those equal sums. So what are all the outcomes that result in a sum of 7? Well, 6 comma 1, 5 comma 2, 4 comma 3, 3 comma 4, 2 comma 5, and 1 comma 6. And again, I can't emphasize enough that even though something like 4 comma 3 and 3 comma 4 seem like they're the same outcome, they aren't. Do they both fall into the category of a sum of 7? Yep. But in this case, right, we got a 4 on the first die and a 3 on the second, and in this case, we got a 3 on the first and a 4 on the second. All right? So, letter B. What is the probability of getting a sum of 7? All right, well, we know that there are a total of 36 outcomes. We know that 1, 2, 3, 4, 5, 6 of them land in the category of getting a sum of 7. So we have 6/36. There we go. Or if you want, you could reduce that down to 1/6. You could also come up with the percent if you wanted. It's something like 16.6%. Now again, that's only on one throw. That's not on 30 throws or whatever we did in that simulation. Let's take a look at letter C. Is it more likely that you would get a roll, that you would roll a sum of 4 or a sum of 9? Justify. So which is more likely? Would I get a roll of 4 or would I get a roll of 9? If I go back a couple screens, right, and I look at actually my results, right, my 4, I had 3 of them. My 9, I had 2 of them. But that was just when I was rolling the die, right? When pure luck was kind of like showing me what was going on. There are my numbers again. Right, what I'd like you to do is try to use probability to figure out which one of those is more likely. All right, well, let's just come up with all the outcomes that give you a sum of 4. And what would those be? That would be a 1 and a 3, a 2 and a 2, and a 3 and a 1. There are no other ones that when I add them together are going to give me a sum of a 4. For a sum of a 9, right, that's going to be a 3 and a 6, all right, a 4 and a 5, a 5 and a 4, and a 6 and a 3. Now really, just even based on those, you could say that the 9 is more likely because they simply are more equally likely outcomes that fall into that category than in the category of having a sum of 4. But we could actually come up with the probabilities themselves. Let me extend the page a little bit. All right, I could say, well, the probability I'm going to get a 4 is 3 out of 36, and the probability I'm going to get a sum of 9 is 4 out of 36. So the sum of 9 is more likely. Not a lot more likely, but a little bit, just a little bit more likely. Now let's look at one last piece, letter D. If 2 dice were rolled 27 times, how many sums of 9 should we expect? Now, of course, if I rolled 2 die 27 times, there is, of course, a chance that I would never get a sum of 9, that it would never happen. So how many should we expect, right? Pause the video now and see if you can think about this a little bit. All right, well, let me move this over. First, let's take a look. The probability of rolling a 9 is 4/36. Now, one way to think about that is if I rolled 2 die 36 times, I would expect 4 sums of 9 to occur. Right? That's one way to think about it, right? So, if I roll 36 times, I would expect 4 of them to be sums of 9. But they say I roll 27 times. So that makes this a little bit harder. And what I really want is I want a ratio that is equivalent to 4/36, but with a 27 in the denominator instead. So what I'm going to do is I'm going to reduce this fraction, right? 4/36 reduces down to 1/9. All right. Now really, what does that 1/9 mean? That really means 1/9 of the time. And by the way, this 9 here has nothing to do with this 9 here. Please don't think that the probability of rolling a 7, sum of 7's 1/7, and the probability of rolling a 2 is 1/2. We know that's not the case, right? So the probability of rolling a 9 is 1/9, which means 1/9 of the times, 1/9 of all the times that we roll, we would expect a sum of 9. So if we've got 27, it's simply going to be 1/9 of 27, and we would expect 3 times. Now, another way to think about it is literally by saying, all right, well, the probability is 1/9. Let me convert that so that its denominator is 27. That would be 3/27, and that would mean I would expect to roll a sum of 9 3 times. All right. Probabilities really not only measure the chance that something's going to happen, but the fraction of how many overall times it's going to happen. So we expect to roll a 9 1/9 of the time. On the other hand, we expect to roll a 7 1/6 of the time. So let's say I rolled dice 12 times. 12 times, 2 dice, 12 times, right? 1/6 of those times, I should get a roll of 7, which means 2 times. 1/6 of 12, 12 divided by 6, would give me 2 times that I should roll a 7. All right, so let's wrap it up. I like to always do this lesson at the Math 7 level because it is a great example of a compound event, one that I wouldn't really want to use a tree diagram on. I mean, I could. You'd have 6 branches, and then from each one of those 6, you'd have another 6 branches for a total of 36, right, outcomes. But that would be awfully ugly. This is a great example of a place where using a table of outcomes can really be helpful because you've got 6 and 6, and you can keep track with those ordered pairs. The first number is what you rolled on the first die. The second number is what you rolled on the second die. Real easy. And then what's really cool is even though there are sums that go all the way from 2 to 12, right, some of those sums are much more likely than the others, the ones right in the middle. You know, a sum of 7, a sum of 6, a sum of 8, those are going to happen a lot, versus sums at the tail end, 2 and 12, aren't going to happen nearly as much. All right, we're going to work just a little bit more with probability in the last lesson in this unit, lesson number 5. For now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.